Okay, so our paper is evaluating large language models for automated serverless workflow generation. This is joint work with my colleagues from our university. Okay, so we are working mainly in serverless workflows. We have AFCL serverless workflow system. Now another one, Florca, which will appear this year. But what we have a problem is that we developed a tool or system to build the workflows, but then when we try to build some more complex functions, we realize that there are challenges inside the function. So to code the functions, not to code the workflow itself. So let's say if we want to split some PDF, or if we want to convert a PDF in English into German audio voice, then we may need to parallelize, but this is easy in the workflow. But then we need to use some OCR service and translate service and the text-to-speech services. Then we need to code access to the storage and so on. So many challenges are needed to be solved during the development of the functions. So mainly when to offload the computing outside of the functions, we call the backend as a service. So these cloud services, and usually they have incompatible interfaces. There are many limitations from the cloud providers in terms of rate or size of the inputs. Then synchronous, asynchronous execution, which should be correctly handled. And if a workflow fails, then we don't know mainly where is the failure. So the debugging is also challenging, and this requires significant engineering effort. So nowadays is everything is let's try LLM. So we follow the same approach to use LLM to how automate the workflow development, in particular function development, and to test if it works or not. So our long-term goal would be to develop an LLM-powered system for serverless service composition automation. And in this paper, we started first to try to analyze different LLMs, their performance, how good are they for this purpose. We tested 4 different LLMs: Claude, Sonnet, sorry, not Sonnet is wrong, GPT, Mistral, and Llama. What we used in our work is we used our framework that we are developing to automate the loop, which is in 2 parts. The first part is how to describe the workflow so that we map the needed path services, like I showed, like a pipeline. And so this would be the structured representation. We created an ontology to describe the workflow. So we want to show to our framework, I have English, I was PDF, convert into German audio. So to find or to describe in this case, to find is our target at the end, but this is not part of this work. And then we describe the input and output between each service and their constraints. And then once we have description of the workflow, then we give this description to the LLM. LLM generate executable code based on the specification of each service that is needed. Then we run this generated code, and if the execution fails, we return back as a loop back to the LLM, and this either the workflow runs or finishes, or we set some, I think, 10 iterations, because at some point the LLMs will not find a correct solution. So we had to set some 10 iterations. Then we have we set 4 research questions. So what is robustness and convergence of the LLMs? How much interventions by the users is needed? after the errors appear, then quality of the generated code and how the code runs across the providers, because the different providers offer the same path services. So we detected two types of errors. One in general programming errors, and here mainly Llama was the worst, and the GPT and Mistral slightly better and Claude was the best one. So here we had file handling mistakes, parsing, function misuse, and so on. So different standard errors of programming, which you can check in the paper details. In the cloud specific errors, data handling issues with services or API misuse, incorrect job handling, and here also Claude had some errors, but mainly again Llama, Mistral, and GPT had also these kind of errors. So to answer research question 1, Claude was the most optimal solution, while the others were worse. Then for manual intervention, we detected 3 core interventions that were needed. So LLMs either resolve errors within a few iterations, or they never resolve. So they go into a loop and they always return the same error. They cannot repair. And here are the results. So let's say for Claude, GPT, Mistral, and Llama, we changed also the temperature and we measured up to 10 iterations. So we see Claude was up to 2 iterations regardless of the temperature, while GPT was worse, but still okay until 5 iterations. And let's say Llama was the worst one. Oh, sorry. So that when we increase the temperature, GPT was improved. So here you see there is no up to 10, but up to 5. That is all that we detected. And especially problem was with the complex workflows, also with poor documentation of the SDK. And for the research question 3, we had 5 senior software engineers, those who work for our group. So, of course, they are good, otherwise they would not work. So we trust them. So they detected, they analyzed the generated code, and they detected unused imports, hard-coded constants, and limited modularization. There were so many that created try-catch blocks, which without meaningful recovery logic. Then difficulties were for asynchronous job state, and in general, the automation is okay, but still required some refinement and manual review. And finally, when we tested for research question 2 consistency across cloud providers between Amazon and Google, so cloud was most consistently generated most consistent code for both providers. GPT succeeded roughly 50%, Mistral only 5. We did not test Llama here because it did not produce at all on Amazon solution, so we did not try on GCP. So in general, more refinement iterations were needed on GCP rather than on AWS, and we believe that this is because of outdated or depreciated GCP APIs. So we conclude that Claude was the best option, so we would continue with Claude, and automation is good, but still requires some manual action. Yeah, this would be. I think I'm wrong time. Yeah.
Yeah, perfect on time.
Our work. Yeah. So if you have any question, please.
Do we have any questions?
Any questions? No questions in the room.
Okay, so
Good afternoon, my name is Florian PETRUSEL. Together with Pedro Antonio García López, we will discuss the benchmarking of serverless AI architectures, focusing on RAG system performance and long context inference. To set the baseline, we must understand the difference between these approaches. Traditional RAG relies on external knowledge queries and use chunk-based text retrieval. On the other hand, long context inference allows the direct ingestion of the entire PDFs, granting the model the ability to process millions of tokens simultaneously. The first architecture is modular RAG, which gives us full control over the data lifecycle. During ingestion, documents go through a fragmentation model with chunk size of 1000 characters. Then, OpenAI text embedding 3 large models generate 3072 dimensional vectors, which are stored in Pinecone. During the query cycle, the user's prompt is transformed into a search vector. Using cosinus similarity, Pinecone locates the top k equal 10 vectors with the closest angle, extracts the plain text from their metadata, and discards the numerical coordinates. Finally, we inject these 10,000 characters of consolidated into Gemini to generate the precision response. The second approach is managed RAG, which operates as a black box. In the ingestion process, the administrator creates a file search storage and simple uploads documents, while the platform internally handles fragmentation, embedding, and storage of vector database. For the query process, the user asks a question and Gemini model performs search and generation in a completely opaque way to deliver the answer. Our third architecture is long context inference. The user attaches the PDF document along with his question. The system will load into memory the entire document without any partial fragmentation. Why is this possible? Because it supports 1 to 2 million tokens in memory. AI performs a complete analysis of the entire document and ultimately returns the response with high precision. We choose AWS Lambda for our environment because it allows us to evaluate this architecture as a completely stateless runtime. This is key for 2 reasons. First, it allows us to measure the pay-per-use model with high accuracy, capturing the exact cost and delivery time for each individual query. And secondly, it allows us to discover typical bottleneck of serverless technology, such as a famous cold start that traditional virtual machines often hide. To carry out the test efficiently, we built an automated test bench. The workflow starts in the local environment with data reading, uses AWS Lambda to interact directly with the selected architecture. Finally, the system executes metrics extraction and saves the results, making a continuous loop for each row on the test bench. To evaluate the results impartially, we implemented an LLM judge. Evaluative artificial intelligence reads the response of generated AI model and compares to the predefined baseline through reference response. Then adds score accompanied by a detailed justification, explaining why that score was given. By testing 142 pages medium-sized documents that lack indexation and structure, long context achieved high quality with a score 9.6, but cost and latency remained unaffordable. Modular RAG proved to be the most robust design with an average accuracy, 9.7, as it successfully insulates important text and handles poor manual formatting very well. Meanwhile, managed RAG showed an irregular performance with a score of 8.4, penalized by the lack of a documentary index for its search engine. The 300 pages expansion revealed the limits of scalability due to context fatigue. For long context, both cost and latency become completely unviable, reducing its average quality to 5.6. Modular rack reached the most efficient speed but suffered from low quality, getting only 4.1. In this scenario, the managed rack became the optimal choice, maintaining high reliability and 6 accuracy despite higher latency. Based on the evaluation results for both short and long documents, let's look at the comparison. As we have seen, we face a clear trade-off where you can only choose 2 of the 3 advantages. Modular rack offers low cost and low latency, making it fast and cheap, but with less accuracy. The managed rack offers low cost and high accuracy, but penalizes latency. Long contexts provide low latency and higher accuracy for medium-sized documents, but requires very high computing cost. At this point, we can improve the accuracy of modular rack by adding multiple recovery rounds from the vector database. Initially, it retrieves 10 fragments, top k equal 10. If we set a maximum of 8 rounds, we can retrieve up to 18 fragments. This makes it more accurate, but it's a balance. We gain accuracy, but costs rise, and latency, though still acceptable, is no longer as fast. In the future versions, it will be interesting to implement this using local databases such as LanceDB or more advanced systems like GraphRack, which provide even higher recovery accuracy. In conclusion, to dismiss rack completely is a mistake, as long context loses its viability in cost and latency after 150 pages. Our findings are supported by recent scientific literature, such as the LARA 2025 study by Quan Li, which also confirms the need for hybrid routing. Therefore, the most viable solution is a smart routing deployed in production. When using a router in AWS Lambda connected to a web interface, the system evaluates the query in real time and directs it to the most optimal architecture. This hybrid approach combines the speed and low cost of rack with the accuracy of long context. Before finishing, I want to talk about our methodology and our future work. You might wonder why we focus it exclusively on Gemini. We chose Gemini family because it was the only mature model offering a native 1 to 2 million token context window, which was a technical requirement to test the long context architecture with 300 pages PDFs. Can we evaluate other models with this current AWS Lambda code? Yes, our serverless architecture is high modular and fully compatible with future Gemini version. However, to evaluate technologies from other companies, we will need to make slight adjustments and prior configuration to their specific rack systems for them to work correctly. Looking ahead in the coming months, I plan to develop a new research project that integrates the different technology. The objective is to evaluate both Pro and Flash models tiers, testing the most advanced models currently available, such as Cloud, GPT, and Grok. We will focus strictly on the automotive domain to see how efficiently this architecture can limit AI hallucination when restricted to specialized data. Thank you very much for your time and attention. You can access my code by scanning this QR code. On my GitHub profile, you will also find a link to my personal website. If you want more context about this research, you can go to the project section, and in the first card you will find the PDF of my thesis. Since this research was born from that work. If you have any questions, don't hesitate to contact me via LinkedIn. Thank you very much for this opportunity, and thank you very much to Pedro García for all his support.